Assalamualaikum and good day to our lecturer Dr. Nur Shahida and to everyone watching. My name is Nur Mashita Afif Fitri binti Rosli. My matrix number is E25A4043. Today our group will be exploring the dynamic world of geochemistry. At its core, geochemistry is the study of the tools and principles of chemistry to explain the mechanism behind major geological systems. We are not just looking at rocks or water in isolation. We are looking at the chemical dialogue between them. Whether it is the weathering of a mountain or the nutrient exchange in a handful of soil, this process dictates the habitability and composition in our planet. Our presentation is divided into three critical pillars. We will first examine how rocks break down and release elements through weathering. Next, we will see how these elements are transformed within the soil matrix. Finally, we will look at how water acts as the primary vehicle for chemical transport, influencing everything from pH levels to mineral solubility. Before we go to the main process of geochemical, I want to explain about the geocycle. The starting point is magma and igneous rock. We begin in the Earth's interior with magma through the process of crystallization. This molten rock cools to form igneous rock. This is the primary source of most elements on the Earth's surface for weathering and transport. Once these rocks are exposed to the surface, they interact with the atmosphere and hydrosphere. This leads to weathering and transportation. Chemical and physical forces break the rock down, turning solid mineral into sediment or dissolved ions in water. This is a key geochemical bridge where minerals from the lithosphere into the water cycle. After that, the path to sedimentary and metamorphic rock diagnosis. As sediment accumulate, they undergo diagnosis, a geochemical process of compaction and condensation to become sedimentary rock. Finally, if these rocks descend deep enough, they undergo anastasis, which is partial melting or total remelting, returning to a state of magma. This completes the cycle, showing that the Earth is essentially a massive chemical recycling system. Now it's time for my friend to continue explain more about the geochemical process in soil, rock and water.
Assalamualaikum. My name is Noor Belkis Shamira binti Hassan and my number metric is E25B3645. So today I want to talk about geochemical processes in soil. So soil geochemistry. This is truly multidisciplinary field that acts as the bridge between geology, chemistry, and environmental science. Our goal is to understand the chemical composition and the invisible processes occurring within the soil matrix, focusing, focusing specifically on soil formation, nutrient cycling, and the behavior of contaminants. So, what exactly is soil? Soil it is a composite of four pillars, which is minerals, organic matter, water, and air. In geochemistry, we look at elemental composition, which is focusing on major elements like silicon, aluminum, calcium, iron, and magnesium, alongside trace elements like zinc, copper, and lead. Second is mineralogy. The distribution of these elements depends on the parent rock, the climate, climate and the vegetation. Lastly is the metric. Clay minerals and oxide are the engine room of the soil, controlling how gaseous and trace metals are retained or moved. Soil is born to weathering, physically, biological, and chemical weathering. Break down primary minerals into secondary minerals. A classic example is the weathering of feldspar into kaolinite. Using the chemical equation. This process releases essential dissolved ions and creates secondary minerals that form the structure of our soil. The behavior of elements is governed by two main thermostats, which is pH and redox conditions. In acidic regions such as Kelantan, Malaysia, low pH increases the solubility of metals like aluminum and manganese, which can lead to toxicity. Second is redox. This measures the tendency to donate or accept electrons. It is influenced by moisture and oxygen. For example, it dictates whether iron exists as Fe2 plus or Fe3 plus, which significantly alters its mobility and how plants can absorb it. Soil have the incredible ability to hold onto nutrients. This is measured by cation exchange capacity, or we call it as CEC. This the sum of exchangeable cations a soil can absorb, measured in CMOL or kg. Through ion exchange and absorption, clay and organic matter act as a reservoir, releasing nutrients to plants or potentially looking away contaminants so they don't reach our groundwater. Geochemical processes dictate bioavailability. For instance, in acidic soil, phosphorus often binds so tightly with iron or aluminum oxides that paints cannot reach it. We also monitor element mobility to see how heavy metals accumulate near industrial areas or how nutrients leach away, which is vital for instance, in acidic soils, phosphorus often binds so tightly with iron or aluminum oxides that planes cannot reach it. We also monitor element mobility to see how heavy metals accumulate near industrial areas or how nutrients leach away, which is vital for sustainable agriculture and fertilizer optimization. Geochemistry isn't just for plants, it's for bridges to strength and stability. Minerals like smeg Geochemistry isn't just for plants, it's for builders too. Strength and stability. Minerals like smectite Smectites cause soil to swell and shrink, affecting stability. Processes like fermentation and diagnosis can increase shear strength. Second is permeability. Small clay particles and mineral qualities can reduce hydraulic conductivity, impacting drainage. Lastly is erosion. The chemical glue or binding agents in soil determine how easily it erode, erode, erodes or is transported as sediment. So, in environmental material and perspective, how do we apply this? So, we identify heavy metals or radionuclides using techniques like XRF or X-ray fluorescence and ICP-MS. Second is geochemical mapping. Geochemical mapping distributes anomalies, either natural or human-made, that guide us in remediation. Lastly is prospecting. We can actually find mineral resources by surveying the chemical signatures in the soil above them. In summary, geochemical processes in soil links, links to geological and biological processes, whether we are assessing soil health or for security, monitoring pollution, or ensuring the stability of our infrastructure. Understanding this chemical reaction is essential for sustainable land use. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Aizalin Asban bin Abdurrahman and my number metric was E25A3660 and I will present you my part, and that was geochemical process in rock. Geochemical process in rock refer to the natural chemical change and reaction that occur within rock over time. Some of the processes include weathering, erosion, sedimentation, metamorphosis, and the rock cycle. This process control how rock form, transform, and break down as part of the Earth dynamic system. First one was igneous process, deep earth. Fractional crystallizations as magma cools, minerals with higher melting point crystallize first and settle out, changing the chemical leftover of the remaining melt. Partial melting. When a solid rock begins to melt, only certain minerals liquefy. This usually enrich the melt in silica and incompatible elements like potassium or sodium compared to the source rock. Point number 3 was magma mixing. Two distinct magma bodies meet and blend, creating a hybrid geochemistry that doesn't match at the original source. The second was weathering and alteration surface. The first point was oxidation. Mineral containing iron or manganese react with oxygen. A classic example is rusting of basalt or pyroxene. The second part was hydrolysis, the chemical breakdown of a mineral due to reaction with water. This is how primary mineral like feldspar transform into clay minerals. The third point was carbonation. Dissolved CO2 in rainwater forms weak carbonic acid H2CO2, which dissolve carbonate rock like limestone and marble. Metamorphic process. Solid state crystallizations, existing mineral grains change size and shape. Neomorphism, new minerals form from the old one. For example, shale clay rich can transform into garnet siege through dehydration reaction. The third point was metasomatism. The chemical composition of a rock is altered by hydrothermal fluid thought mineral-rich water passing through it, often depositing valuable metal like gold or copper.
Hi, my name is Muhammad Akif Nasrullah bin Ismail. My metric number is E25A3607. Now I'm going to talk about sedimentary and diagenetic process. The journey of a sedimentary rock begins with liquefaction, which is the geochemical combination of compaction and cementation. Compaction is a layer of sediment accumulate. The shear weight of the overburden squeeze the grain together, reducing the pore space. While cementation is a process where chemistry happens. Minerals like calcite or quartz precipitate from groundwater directly into this remaining pore space. These minerals act as a natural glue, bonding the grains together. Without this geochemical precipitation, the material will remain lost, sand or seed. Next is ion exchange. This is a critical process occurring within the sedimentary layers. Clay minerals are particularly active. They have the ability to swap ions with the surrounding groundwater. For example, a clay mineral might exchange its sodium ion for calcium ion from the water. This process is a two-way street. It alters the mineralogy of the rock and simultaneously change the chemical composition of the groundwater flowing through it. Next is absorption and adsorption in rock. We look at how rock interact with fluid through absorption. Absorption is the process by which a rock takes a water, iron or gases into its internal pore space or its actual mineral structure. The chemical solution penetrates the rock through fracture and microscopic pore. Once inside, ions such as calcium, magnesium, and potassium can be incorporated into the structure of minerals like feldspar or clay. For example, a classic is a porous limestone. When it absorbs water containing dissolved calcium bicarbonate, it undergoes a slow chemical alteration. The important is not just for physical change. It contributes to rock weathering and help the rock remain elements. This element can later be released back into the soil or groundwater, acting as a chemical reservoir for the environment. Next slide is a geochemical application in rock. Let's look at how we apply this forensic science of geochemistry in the year 2026. We use the chemical fingerprint of rock to solve real-world problems. First is a resource exploration and mining. Geochemistry is our primary tool for finding invisible wealth. Mineral prospecting is we look for pathfinder elements. For instance, finding high concentration of arsenic or antimony in surface rock can act as a trail leading us to hidden gold. Next is ore grading. Using SRF, X-ray fluorescence, miners can test rock chemistry on site to instantly determine ore purity, which saves time and massive amount of energy. Next is tectonic and magnetic reconstruction. Rock are the Earth memory. Fingerprinting is by analyzing trace elements. We can determine if a rock was formed at a mid-ocean ridge or a volcanic island arc. A geochronology is when we use the decay of radioactive isotope such as uranium lead system to determine the exact age of a rock, dating events from millions or even billions of years ago. Next is environmental and climate science. We are now using enhanced weathering, grinding up silicate rock like basalt to react with atmospheric CO2, locking the carbon away into a solid mineral. Paleochematology is by measuring oxygen isotope ratios in sedimentary carbonate rock. We can reconstruct what ocean temperature were millions of years ago. Last but not least is engineering and infrastructure. For construction safety, geochemical testing prevents the alkali silica reaction or a concrete cancer by ensuring rocks used in infrastructure won't react with cement and cause cracking. Next is a waste disposal. It is also essential for designing nuclear waste repositories, ensuring the rock chemistry will remain stable and contain radioactive mineral for over 100,000 years.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Zulfikar bin Abdul Haris, and today we are going to dive into the fascinating world of the aqueous geochemistry, or also known as geochemical process in water. Basically, water is more than just a solvent. It's a dynamic medium where constant chemical transformation occur. Our focus today is on the geochemical process in water, the fundamental reaction that shaped our environment today. So basically, what exactly do we mean by water geochemical process? Essentially, this involves water reacting naturally with its surrounding environment, including rock, soil, the atmosphere, and even the living organism. This water geochemical process determines how the dissolved element and mineral will be formed, move, and change within the water. So, to understand this interaction, we categorize them into seven major processes. Throughout this presentation, we will explore about weathering, dissolution and precipitation, ion exchange, redox reaction, hydrolysis, adsorption and desorption, and also about evaporation and concentration. Each of these plays a specific role in defining the chemistry of the water we find in our river, lakes, and underground aquifer. The first of all, let's look at the weathering. This is the starting point where rock and mineral break down near the Earth's surface. We categorize we categorize this into physical and chemical weathering in geochemistry. We are particularly interested in the chemical side, reaction like carbonation and oxidation. Take feldspar for example, which is a common mineral in granite. Through weathering, it releases essential nutrients into the soil and groundwater, illustrating how of our water chemistry. The next thing is the duo of dissolution and precipitation. This process controls the migration of minerals. Dissolution occurs when water actively dissolves minerals, pulling them into the liquid phase. However, when water becomes oversaturated, meaning it can't hold any more iron, precipitation occurs, and mineral will form as solid. This balance is critical for controlling the overall composition and mineral content of water body. Moving to the next point, which is ion exchange. This refers to swapping of ion between the water and solid surface, usually clay or organic matter. Common ions involved include sodium, calcium, and potassium. A classic example is seen in coastal aquifer, where sodium from seawater might replace calcium on clay surfaces. This process is a vital natural filter. It significantly influences how pollutants, especially heavy metal, move through the subsurface. For the next point, the redox reaction or reduction oxidation involves the transfer of electron. This change the oxidation state of element, for instance, the transformation of dissolved iron into iron ferrum into solid iron oxide, ferrum 3 plus. This is important because it doesn't just change the color of the water, it immobilizes element, taking them out of the water and turning them into solids. Understanding redox is critical for managing water toxicity and solubility. For hydrolysis, hydrolysis is a slow but powerful process where water and weak acid react with silicate mineral breaking down into a clay mineral. This reaction, this reaction is what breaks down the complex rock into clay mineral like kaolinite. It's perhaps the most essential process for regulating the chemistry of the Earth's crust and our surface water over a long geological timescale. Now, let's discuss about adsorption and desorption. Basically, adsorption is when dissolved substance like nutrient or contaminant stick to the surface of a solid. It is a great temporary fix for immobilizing pollutants. However, the reverse process, desorption, can lead to sudden contamination in if the water chemistry change, releasing those trapped substances back into the flow. And finally, we have the evaporation and concentration. When heat removes water from a system, the remaining ion become more concentrated. We see the impact of the most clearly in agriculture in areas with heavy irrigation and shallow groundwater. High evaporation can lead to salinization, making the land less fertile. This process is also responsible for forming massive evaporite deposit like salt flats. In summary, these seven geochemical processes work in harmony to define the quality and character of water on our planet. From the breakdown of mountain via weathering to the microscopic exchange of iron on the clay particle, geochemistry is the key to understanding our most precious resources.
All right. Hello, my name is Arifando Arifin, and my matrix number is E2583678. And I'm going to talk about our chemical process in soil, rock, and water in conclusion, or a very short uh, okay here. As you can see, geochemical studies of soils, rock, and water um, are essential for understanding the compositions, process, and interaction within the earth. system. Each of these components provide unique but interconnected information about how elements are distributes and transform in the natural environments. When studied together, they offer a comprehensive picture of both surface and subsurface geochemical processes. However, in soil biochemistry reflects the combined influence of weathering, biological activity, and human impacts. As rock break down over time, the minerals are transformed into soil, carrying with them important chemicals signature. This signature helps scientists understand nutrient availability, soil fertility, and presence of the contamination. Soil also act as a medium that uh, stores and transfer elements between rock and the water system. Then rock geochemistry, on the other hand, focus on the origins, compositions, and evolution of earth materials. By analyzing rocks, scientists can determine the process that form them, such as volcanic activity, sedimentations, and metamorphisms. Rocks serve as a primary source of the many elements found in soils and water, and their chemical composition provides a baseline for understanding natural variations in the environments. Water geochemistry play a critical role in the movement and distribution of the chemical elements. As water flow through rocks and soils, it dissolves minerals and transfer transport ions from one location to another. This process influences water quality, ecosystem health, and cycling of nutrients. Studying water chemistry helps identify pollution source, understanding ground system, and assess environment change. As you can see on the slide, in conclusion, the integration of soil, rock, and water geochemistry provide a holistic understanding of Earth chemical systems. These three components are closely linked with each influencing the other through continuous natural processes. By examining them together, scientists can better assess environment's conditions, detect contaminations, and locate valuable natural resources. This integrated approach is crucial for sustainable and environmental management as it support informed decision making in agriculture, mining, water resources management, and environmental protection. Ultimately, studies help us understand how the earth functions and how human activity may impact its delicate balance. So that's all from me. Thank you.